All right, so in the unit, we've started looking at how the derivative of our function can help us find things about the function. For instance, on the first day, we were looking for those critical values, or those critical points, which we found by seeing where the derivative equaled 0 or where it was undefined. And those critical points combined with the endpoints helped us figure out the absolute max or min. So there's some information we could find about a graph just from its derivative without using a calculator. And today we're going to look at some more things that we can find from the equation and from its derivative. So today is going to be about the derivative test, the first derivative test, because there's two of them. But before we go on to the first derivative test, we're going to set up kind of the background that's going to lead us into it. So we're going to be talking about increasing and decreasing intervals and how you know when you have them. So we're going to say if a function has a positive slope, and a positive slope for a graph happens when the derivative is positive, right? When it's evaluated and we get a positive value, and that means the f prime of x is greater than 0. Then the function is increasing. It has an upward slant. If a function has a negative slope, this means that f prime of x is less than 0, then it is decreasing. All right, so we're going to go ahead and do an example with that. So we're going to find the increasing and decreasing intervals for f of x equals x to the 4th minus 4x to the 3rd plus 2. And so I need to be able to find my derivative, and then I need to evaluate my derivative so I can see where it's positive or where it's negative. So that's my function. My derivative would be 4x to the 3rd minus 12x squared plus 0. So I'm going to go ahead and set my derivative equal to 0, because if I know where the derivative equals 0, then I can figure out where it is not increasing or decreasing. It's doing neither of those things. So that would be where it's like transitioning from one to the other. It's kind of like when we were doing rectilinear motion and we took the velocity and we set it equal to 0, so we could see where it transitioned from moving left to moving right, or vice versa. So that's very similar to what we're doing right now. So I'm going to factor out the 4, and I'm going to factor out an x squared as a GCF, and so that means that left over, I have x minus 3. So x equals 0, x equals 3. So that means that very briefly at 0 and very briefly at 3, our graph goes horizontal, has a slope of 0. And that might be in between. It goes from decreasing to increasing, or it switches from increasing to decreasing, or it's going up and it levels off and then it keeps going up. We've got different options there. So what I'm going to do to figure out exactly what's happening is I'm going to make a sign chart just like we did when we had velocity, and then I'm going to pick numbers on that chart to plug in. Again, just like we did when we were dealing with velocity. So if I plug -1 in, I can plug it into any of these derivative equations. It doesn't matter which one. I think the factored form is the easiest. So 4 times -1 squared, if I'm squaring it, that's always positive. So positive, and then -1 minus 3 is a negative. So when I multiply those, I get a negative. If I plug in 1, again, that's going to be positive. 1 minus 3 is negative. And then if I plug in 4, again, that's going to be positive and positive. So that means that this graph, if this were a velocity problem, we would say it's moving left and then it rests, and then it's moving left and then it rests, and then it moves right. That's what we would say. Well, we're talking about an increasing or decreasing graph. We're not talking about a story problem. So we're going to say it slants down, which means it's decreasing, and then it levels off. at 0, and then it decreases again, and then it switches from decreasing to increasing. Okay, so I'm going to go ahead and write those answers down here. Increasing from 3 to infinity, decreasing from negative infinity to 0, and then 0 to 3. And when you're working on these problems for like an AP exam and you're justifying your answer, the only justification you need here, the sign chart does not count as a justification. That is us making the math work for us as high school students or as people who need to think about it more simply. For a mathematician, they're going to say it's increasing because the derivative is greater than 0. So we're going to say because f prime of x is greater than 0 because it's positive. And here it's because f prime of x is less than 0. So that's how we can tell about the increasing and decreasing intervals. And I went ahead and I graphed this, and I just wanted to show you. So I plugged in this graph. We're going to be talking more about how to make a window that fits what you want, but what I did is I just went ahead and I looked at the table, and I knew that I was looking at values around 0 and 3, and I could see that 3 was negative 25, and so I just went to negative 30, because to me that was like big enough to be able to see everything. So if I look at my graph, you can see it's decreasing. At 0 it levels out, and then it decreases again, and then it switches to increasing. So we can see all of that from that graph, so our answers make sense. Okay, so now we're going to talk about the first derivative test, and then we're going to use the first derivative test to fit. I just spelled first like that. Then we're going to use the first derivative test to finish the problem. Goodness gracious. Okay, first derivative test. Okay, the first derivative test has 3 situations. So we're going to say given C, and the C that I'm talking about here is a critical point. A critical number or a critical point of a continuous function and then these are the 3 scenarios. If f prime of x changes from positive to negative at C, so at that critical value, so we're talking about like here, this doesn't happen, this one changes from negative to positive, but if it had changed from positive to negative at that number, then f has a local max at C. And you could even draw a little picture of this off to the side. If your graph is increasing and then switches to decreasing, you do have a max there. So this would be like f prime of x is greater than 0, f prime of x is less than 0, and if you make that switch, then you have a local maximum. All right, if f prime of x changes from negative to positive at C, then f has a local minimum at C, and that's what we have in this case. We switch from negative to positive. So if you are decreasing and then you switch to start increasing, that would be a minimum point. And then third, if f of x does not change signs, sorry, f prime, if f prime of x does not change signs at C, then there is no local min or max at C. And so that happened in this problem. It was decreasing and then it continued decreasing, and we could see when we looked at the graph that there was no min or max there. But we did have a min down here because it does switch. Okay, so for this particular problem, we're going to say at x equals 0, there is no local min or max. and at x equals 3, there is a local min. All right, and I'm not saying what the minimum is. I didn't find the y-coordinate. I'm just saying the location of the local minimum. If I wanted to know what the local minimum was, I would have to go back to the original problem. And then I could plug in 3 to the original problem as an x-coordinate and find out what my y-coordinate was. Okay, let's go ahead and continue on with some other examples. So, second example, we're going to find the increasing and decreasing intervals as well as the local max and min on this one. So we have f of x equals x to the third minus 3/2 x squared. And I'm going to go ahead and take the derivative of that. So f prime of x is 3x squared minus 3/2 times 2 is just 3. And then I'm going to go ahead and take that derivative and set it equal to 0. And I will factor that to solve it. So 3x times x minus 1. So x equals 0 and x equals 1. And I'm going to make my sign chart. So a number to the left of 0 would be like -1. So if I plug it in here where my factors are, 3 times -1 is negative. -1 minus 1 is also negative. Between 0 and 1 could be like 1/2. 3 times 1/2 is positive. 1/2 minus 1 is negative. A number bigger than 1 is 2. 3 times 2 is positive. 2 minus 1 is also positive. And so that means that this graph is increasing from -infinity to 0 and from 1 to infinity. And it is decreasing from 0 to 1. So I know it's increasing because that's where the derivative is positive. I know it is decreasing because that's where the derivative is negative. Okay, now I'm going to go ahead and write my relative max and my relative min, or local, whichever way you want to phrase it is fine by me. Okay, so here we switch from increasing to decreasing, so that's a maximum. So our max is at x equals 0, and then our minimum switches from decreasing to increasing, and so we're going to say that is at x equals 1. All right, and again, if I wanted to know the x and the y coordinate of those, I would plug those into the original equation. So I'll go ahead and do that because that won't take too long. So f of 0 is 0 to the third minus 3/2 times 0, which is still 0. So the maximum happens at the point 0, 0. The minimum, if I plug in 1, I get 1 minus 3/2, which is -1/2. And so that means that the relative minimum happens at the point 1, -1/2. Okay, we're going to go ahead and do the exact same set of instructions, but we're going to look at a trig function so that you guys can see an example of that. And this time they're going to give us the interval from 0 to 2 pi, because if you know sine graphs, they go up and down a lot, so that's why we can not have a ton of answers. So I'm going to go ahead and find the derivative of this one just like I did with the other ones. Derivative of 1/2 x is just 1/2. Sorry, my sign should have had an x on it. And then the derivative of sine is cos. So I'm going to say minus cos x. And to solve this problem, I just need to set that equal to 0. That was my derivative. So 1/2 equals cos x. And so I need to solve this by taking the inverse of cos x. So x, I can see, is going to be a radian measurement. That's an angle. So I'm going to be looking on the unit circle to see what angle has an x value of 1/2. So if you look at the unit circle and you see where the x values of 1/2 happen, that's at pi thirds and 5 pi thirds. So 0 2 pi, pi thirds, 5 pi thirds. So a number that's between 0 and pi thirds would be like pi sixths. So if I have 1/2 minus cos of pi 6, cos of pi 6 is root 3 over 2. So 1/2 minus root 3 over 2 is negative. A number between pi thirds and 5 pi thirds would be like pi. Cos of pi is -1. So 1/2 minus -1 is going to be 1/2 plus 1. That's positive. A number between 5 pi thirds and 2 pi would be like 11 pi sixths. So I'm just picturing my unit circle and I'm thinking of radian measurements that are, you know, in between these two radians. 11 pi 6, so if I look at cos of 11 pi 6, that would be root 3 over 2. So 1/2 minus root 3 over 2 is going to be negative. Okay, so this graph is increasing from pi thirds to 5 pi thirds, and it is decreasing from 0 to pi thirds and 5 pi thirds to 2 pi. And I know it's increasing there because the derivative is positive. I know it's decreasing because the derivative is negative when you evaluate it. So now I'm going to go ahead and find my relative max and my relative min, or local max and local min, whatever your preference is. So the relative max happens when we switch from positive to negative. So right here we switch from positive to negative, and so that's at 5 pi thirds. And I'm going to have us find the y coordinate just because it's not fun on this one, so practice is always good. And then the relative minimum happens here. We switch from negative to positive, and so that's at pi thirds. Okay, so let's go ahead and take these and plug them back into that original function. So f of 5 pi thirds is going to be 1/2 times 5 pi thirds minus sine of 5 pi thirds. And so this first one is going to give me 5 pi over 6. And then sine of 5 pi thirds is negative root 3 over 2. So here I have minus minus makes a plus. And I can see a denominator of 6 and a denominator of 2. So that means that I need to multiply this by 3 on the top and the bottom to have that common denominator. So my common denominator is 6. And then I have 5 pi plus the square root of 3 times 3. And most people would say 3 square root 3. So it's messy, but we found it. So 5 pi plus 3 square root 3 over 6. The next one's a little bit better because the number we're plugging in is not as messy. So here we're going to have 1/2 times pi thirds minus sine of pi thirds. 1/2 times pi thirds is going to give us pi over 6. Sine of pi thirds is just root 3 over 2. So again, we need that common denominator. And so we have our common denominator of 6. We're going to have pi minus root 3 times 3. And so that is our other y coordinate. So we just have to remember that we can find our maxes and our mins based off of our increasing and decreasing intervals. And increasing and decreasing intervals are a reflection of what our slope is. And slopes always come from the derivative. Anytime we want to go back and reference points on the graph, the points on the graph always have to go back to the original equation. You can't get points on the graph from the slope. This gives you slope, this gives you points on the graph. So we want to always make sure that we remember that.